part series, and today we'll graph a little more complicated rational function. If you remember, the first step is to fully factor the numerator and denominator of the function. So why don't we do that first? And so in this case, you might notice that the denominator can be factored. So you get f of x is equal to x minus 3 in the numerator, but the denominator is a difference of two squares, and it becomes x plus 1 times x minus 1. And step 2 is to cancel like factors from the numerator and denominator. And if there were any to cancel, these factors would become the wholes in our function, but there are no common factors, so that makes it easier. So our next step is, using the reduced or simplified function, find the vertical asymptotes. And if you remember, the vertical asymptotes are simply the values where the denominator becomes 0. So in our first example, we know that if x plus 1 were equal to 0, x would be equal to negative 1, and therefore our equation of one vertical asymptote would be x equal to negative 1. But we have another factor, x minus 1. If we set that equal to 0, you notice we get x equal to plus 1. So this is a little different than our rational functions in our other two parts. Of course, we get two vertical asymptotes. Our next step is to find the horizontal asymptote. And if we look at the degree of the numerator and the degree of the denominator, let's rewrite our function over here, our original function. F of x is equal to x minus 3 over x squared minus 1. We look at the degree of the numerator, which is a 1. We look at the degree of the denominator, which is a 2. And what we have learned is that when the degree of the denominator is larger than the degree of the numerator, the horizontal asymptote is at y equals 0. And so let's write that down here, y equals 0. And that is our equation of our horizontal asymptote. So our next step is to find the x and y intercepts. And if you might remember, the x-intercept is simply when y is equal to 0. So if we set our function equal to 0, we get 0 equals x minus 3 over x squared minus 1. And if we multiply both sides by x squared minus 1, we would get 0 equals to x minus 3, which means x is equal to 3, and that is our x-intercept. For the y-intercept, if you remember, that's when x is equal to 0. So if we substitute 0 for x, we get 0 minus 3 over 0 squared minus 1, and that gives us y equals negative 3 over negative 1. So find that we get y is equal to 3, and that is our y-intercept. And our next step is to check to see if the graph will cross the horizontal asymptote. Now, that might sound unusual to you, but it turns out that to the far left and the far right of these graphs, the horizontal asymptote is an asymptote, as you know the definition. But and that would be to the left of the x-intercept and the left of the vertical asymptote, and to the far right of the vertical asymptote and the far right of the x-intercept. That's where the horizontal asymptote acts as an asymptote. But in the middle, it turns out that you actually can cross it. And so to check to see if the graph crosses it, we have to set the reduced function equal to the horizontal asymptote and solve and see if there's a solution. So if we go back to our original function, we get x minus 3 over x squared minus 1. And you might remember our horizontal asymptote was at y equals 0. So we set this equal to 0, since y is equal to 0 is our horizontal asymptote. And we multiply through by x squared minus 1. And you'll notice when we're done, we get x minus 3 equals 0 and x equal to 3. Since it turns out there is a solution, it turns out the graph will cross the asymptote at that value x equals 3. So it will cross the horizontal asymptote at x equals 3. We'll cross at x equals 3. And so our next step is to connect the known points, and usually we will create a table for each side of the asymptotes, of the vertical asymptotes. And in this case, we have 2 vertical asymptotes, so we'll have 3 sections. So first of all, let's excuse me, let's draw the vertical asymptotes. And if you remember from previously, we have a vertical asymptote at x equals 1 and a vertical asymptote at x equals -1, which we discovered earlier. So let's draw those in. And so you can see we just drew our vertical asymptotes at x equals 1 and x equals -1. We probably should draw our horizontal asymptote, which is at y equals 0, which we discovered that previously as well. So we'll do that. And that's just on the x-axis. And now we could plot the intercepts. If you remember, the intercepts are at 3, 0 for the x-intercept. So let's put that down there. So at 3, 0 is an x-intercept. And the y-intercept is at 0, 3. And that's also all in our table that we have above. And the other thing that we did notice that the function does cross the horizontal asymptote at x equals 3. And we can certainly see that because that's the point we just plotted for the x-intercept. So our next step is to plot the graph on each section of the graph that has been divided up by the vertical asymptotes. So what I've done here, if we look at our table for the first section, goes from -8. The asymptote is x equals -1. So here's our first section. If we plot these points, let's just plot them. Here we have -8 and -11/63. So it's a pretty small number. So it's somewhere over here. Then -6 and -9/35. That number comes down just a wee little bit more. -4, -7/15 comes down a wee little bit more. -2 and -5/3. Well, that's -2 and 1 2/3. So that's about here. And you can certainly see the pattern that's starting to happen, which is it's going to start coming down and never quite reach, get closer and closer, but never quite reach the vertical asymptote. And on the left side here, it's never going to quite reach the horizontal asymptote. And that's our first section of the graph. Okay, so let's graph the middle section. I took the liberty of coloring in the middle section, making it red. So we see that at -0.5, we have a y value at 4.24. So at that's probably about here. And then at 0.3 we already knew about because that was the y-intercept. And finally, at 0.5, we're at 3.66. So it's probably about there, something like that. And let's connect those dots. So we just connected those 3 points. It's kind of, remember, we're making a sketch, it's not exact, but we can certainly see that looks kind of like a parabola that's off center. So that's what it looks like between the two vertical asymptotes. Now we want to plot the points to the right side. The right side is over here. So let's plot those points. We are at 2 and negative 1/3. So that would be down here. And 3, 0 we already have graphed, and 4 and 1/15. So notice how it has now crossed the horizontal asymptote, and it's gone up just a wee little bit. Sorry about that. So here is 4 and 1/15, and then 6 and 3/35 goes up a little bit more. 8 and 1/16 goes up a little bit more, and you can certainly see what's happened is it has come from down here, crossed over, is going up very, very slowly in that direction, comes down that direction, and now we have successfully plotted the graph. I just wanted to remind you that in order to plot the graph, we need to factor the rational equation. We need to find the vertical asymptotes. We certainly need to find any holes. We need to find the horizontal asymptote, the x and y intercepts, figure out if it crosses the horizontal asymptote. And then as we graph it, we graph each section, the section divided up by the vertical asymptote. So we graph the left section, the middle section, and then the right section. And if you do it in steps like this, you shouldn't find it too bad. And I hope you enjoyed this, and I hope you got something out of it. Thank you. And now it's your turn. Here's a problem very similar to the one that we just did. What I'd like you to do is try to graph it. If you have any difficulty at all, go back over the screencast, follow what I had done, and step by step you should be able to graph this problem as well. And that's it for now. Good luck, and see you again next time.